This is a group lab report. Group lab report will be due next week when you come to lab. If you need to coordinate getting together, I would recommend considering this weekend, if that's, even though you're turning in your 8-week lab on Monday, because this lab report will be due next week when you come to lab. Group lab report. Vidic reaction. Vidic reaction covered by video only. Any questions about that video lecture? We'll pick up where we left off at. Decarboxylation of what type of compounds are easily decarboxylated? Yes, that's it. Product here. Like a product here. Thermolysis reaction. Plus CO2, yeah? Basically, we're just going to decarboxylate right here. CO2, this H is one H here, is going to be 2 here. And we lose CO2. Yeah? Because a carboxyl group that has a carbonyl beta, carboxyl group alpha beta is easily decarboxylated. Loss of CO2, and the H moves to the carbon. You see what's going on. Common reaction. Pyruvate is not a beta keto acid. Who was saying that? Who's it? Did you say something about pyruvate?
Yeah, you said that.
I did, but someone said something else about it. Like,
That we've learned pyruvate, but we didn't know it was a
you
beta.
said you've seen it, yeah.
Mhm.
I looked it up. Pyruvate is not a beta keto acid. It's actually an alpha keto acid. And those I don't think decarboxylate readily. So pyruvate is not a beta keto acid. Pyruvate being the anion, but it's the anion of an alpha keto acid. But have you heard of alpha keto acids? Yeah? Okay. So that's just a general name for the type of compound. But beta keto acids are also very common. Ketoacidosis, this beta keto acid down here, is formed in the body when it isn't necessarily done so, but it's forming an acid. You may have also heard of ketone bodies. See, this compound can be referred to 2 different things. It can be called an acid, but it can also be called a ketone. And so it's a ketone body that's formed in the body and generated during if your body goes into ketolysis. And there's a variety of different ketone bodies, ketones that are formed. But many of them, a lot of them also have the acid portion, but for some reason just focus on the ketone part. Not all of them have the acid. Okay, beta keto acids. We will also see on the next page beta dicarboxylic acids. Reaction up here, malonic ester synthesis. If this was an acid here, the diacid, that would be called malonic acid. It's a common name for a dicarboxylic acid with a CH2 in between. This is the diester of malonic acid. And it's called a malonate ester. Malonic or malonate. What do I have written up here? Malonic. Sometimes you may hear malonate ester. It depends on if you're spelling it with IC at the end or 8 at the end, which is different pronunciation. So I would typically, I'm prone to call it a malonate ester. But let's treat this with a base. What's a base going to do? Or nucleophile. But this is an example, another example of a compound like this. 2 electron withdrawing groups with the CH2 in between. It could be just a CH. There could be something else here. By the way, what's the CH2 group called? What's the CH3 called?
Methylene.
Methyl. What's the CH2 called?
Methylene.
I can't quite hear.
Methylene. Methylene.
I still can't hear you.
Methylene.
Methylene. Yes. Y-L-E-N-E. Methylene. So it's got the methylene group between the two halogens. Methylene chloride. CH2Cl2. Common solvent. Also known as dichloromethane. By the way, what's the CH called?
Methine. 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 I don't know.
Methine. You learned these in organic 1?
No. Well, I mean, yes, but I mean, I just reviewed it earlier.
Okay. Because I don't know that I covered that in organic 1. Methine, methylene, methyl. Okay, just here. So the methylene between the 2 electron withdrawing groups. Treat this with base. You're just going to deprotonate here and make the anion. Yeah? Could that act as a nucleophile? Okay? This is methoxide, right? What if methoxide added to the carbonyl?
You kicked right off.
What if we kick the other OME off?
How you think?
It'd be the same thing. So we chose the appropriate base. So if it did do addition to the carbonyl, you wouldn't get anything new. So the OR matches our OR here, so you don't get ester exchange. But we can make the anion, and this is acidic enough that the equilibrium is going to be complete. And then this we throw in something with a leaving group like this, and yeah, we're going to alkylate, and we just made that bond, right? That's just a good old SN2. We first generated our nucleophile. We could have showed such example in organic 1. Well, we can do chemistry here. What if we treat this with aqueous acid and heat? What's going to happen? Well, it's an ester. You're going to hydrolyze your ester. But you got 2 esters. You're going to hydrolyze this to the dicarboxylic acid. Ester hydrolysis. But at that point, it's not going to stop here. This is not going to last with heat, because we know that anytime you have a carboxyl group with a carbonyl beta, what can happen to the carboxyl group? Be decarboxylated. Either one. Let's look at this one. Does this carboxyl group have a carbonyl beta? Alpha, beta. We didn't say the carbonyl had to be a ketone. It could be any carbonyl. One of these is going to be decarboxylated. Now it's symmetrical. It doesn't matter which one you decarboxylate. But only one will. And if we decarboxylate minus CO2, that's your product. You can see how it's drawn. Because just get rid of it. Get rid of this one. This H is effectively going to end up here. And so it's acid CH2, phenyl. Acid CH2, phenyl. It's just been decarboxylated. That will happen with the heat pretty readily. In the end, beta dicarboxylic acids, beta dicarboxylic acid, these also are readily decarboxylated, just like beta keto acids do. Ultimately, what have we made here? We've made a carboxylic acid. But we've added sort of an R group to it. Okay? What if we had taken this acid, which happens to be acetic acid, what if we had tried the same approach, treat this with some type of base, your choice, and then come back with, you can just move those reagents here, this. Can we make that directly? Will the base deprotonate here and make anion?
No.
What will it do instead?
Oh, attack.
It's going to deprotonate that H. That's the more acidic H. They're both alpha H's really, but this H is on oxygen, this one's on carbon. More acidic. Okay? You're not going to be able to do that. This is a common route to eventually making acids which have something else here that came in by alkylation. And you could say, well, let's just make this an ester. We make this an ester, then we can make anion over here. But guess what? Since there's only one carbonyl, it's not as acidic, you're going to have to use something like LDA. Well, in our method, we're using a dummy group, and we're using the weaker base. And so this is just a very common, this is just common, it's just a common sequence that involves more of an indirect approach and the decarboxylation of the other group. Now you don't have to decarboxylate, because you can do other chemistry here as well. But the decarboxylation is a common process or route. Students tend to get a little confused here. It's like, why do I still have an acid? I thought I decarboxylated. Well, it's because you had two acids. You only decarboxylated one of them. Okay, so we did some indirect alkylations, decarboxylation. A little bit more there, more convenient than the direct alkylation, which requires use of stronger base such as LDA. And ultimately, we're alkylating enolates that we're forming. Basic conditions and doing a good old SN2. Okay, we'll move to another reaction that's common with enolates. Alpha condensation reactions. The most common here is the Aldol condensation reaction, often just called Aldol reaction. The condensation typically applies that we're going to produce something that's kind of comes out as a liquid, it condenses out. Very often that means we're going to form water. But it could sometimes be maybe an alcohol. But we are going to form water here. And that's why it's termed a condensation. Like you get condensation on your bathroom window. Water forming on it. That's where it came from. Water was formed. If we take an aldehyde or ketone, again, because all the examples are really aldehydes or ketones. Aldehydes don't alkylate well because they tend to do another reaction more easily. They tend to do aldol. So we may not have seen aldehydes much up there. We'll see aldehydes more down here, especially when we do a mixed aldol. We got a ketone here. If we take two equivalents of this and treat it with some type of base, it could be 1,000,001 different bases, catalysts. We can get what sort of looks like a dimerization reaction, two of these reacting together, and we can get this with an alkene here. Only one carbonyl remaining of the original two. That's two of those. This only has one oxygen. The other oxygen is now been eliminated as water. The aldol reaction gives, it's another way to make alpha-beta unsaturated carbonyl compounds. Here's your carbonyl, alpha, beta, and you see the alkene, the unsaturation. Okay? An aldol reaction gives an alpha-beta unsaturated carbonyl compound, but it doesn't have to be carbonyl. It could be nitrile, or it could be a couple of other similar groups, analogous to carbonyl. So there could be other things other than aldehydes or ketones. We may see examples. Most common is with ketones. Base catalyst. Okay, with the base, we're going to get formation of, and I'll just use phenyl here. We can form some enolate, right? Base takes an H. You know mechanism for acid-base reaction. Enolate. But this is an equilibrium, right? And with hydroxide, the equilibrium is actually, this is fatal. But we can generate a little bit of this. Well, what could this anion react with? Well, a variety of things. But in this reaction, what does it react with?
The other.
Right, it reacts with itself. Because while you got this, you've also got lots of these. And this reacts with another molecule of itself, but at the carbonyl. Electrons up. And that gives it's basically your nucleophile. Yeah, nucleophile adding to carbonyl. But it's a little big. Okay. Let's keep, okay, here we go. That was a nucleophile. It made a bond to carbonyl and electrons up. So that's the bond we just made. Carbon of the enolate adding to carbon of the carbonyl, electrons up. What else is on the carbon of the carbonyl? Another a methyl anaphenyl. Okay? Let's call this phenyl 1. Phenyl 1, yeah. And we'll call that phenyl 2. Is that right? Is that the bond we just made by the enolate adding to carbonyl? Okay. What can happen next? I tell you one thing that could happen is these electrons could come back down and kick that off. Now, very often we don't kick off plain carbon, but that's not a plain carbon because if it gets kicked off, what got kicked off? Stabilized enolate. It's possible. Equilibrium. But if we keep going ahead, what can happen next over here?
Hydroxide comes in and takes H.
Hydroxide takes what H?
The methylene.
Possible, but this is already an anion. The molecule is already an anion. It is possible to make a dianion. Yes. We've got water around. Not necessarily. Even if there's no water here, we generated water when we made this, right? When hydroxide takes an H, we generate water. But very often this is done in a protic solvent, maybe like ethanol. And we can take H from water. We could also take H from ethanol. Solvent. So I'll take it from water. Let me move over. Well, I'll stay down a little bit. And so we get plus what?
Hydroxide.
plus hydroxide, okay? Now, could this go backwards? Could hydroxide take that H? Yeah, equilibrium. Now, there's another way to do this. We'll show the alternative way after we complete this way. What next? Now let's take the H again, because this is alpha CH. These have some acidity. The base that you generated can take the H, leave electrons behind. Plus what? Plus water. This is our enolate equilibrium. Could this take an H back?
Yes.
Certainly. And actually, which side is favored here? That's actually favored. Whenever you make enolate with only one carbonyl using an oxygen base, you're making only very little of this. Because that's 20 and this is 16, 20 is favored. But we can make a little of this. At this point, what can we do? And we're only one step away to getting home.
You kick off the OH or you protein.
Anytime you can make a pi bond and kick off a leaving group, now I shorten that, the full statement is anytime you can make a pi bond using a lone pair and kicking off a leaving group, easy to do. And just about any leaving group that you've ever seen minus can leave. You're typically not going to kick off just a plain carbon. Have you ever seen OH be minus? Yeah, this is very easy. And what does that give? What is this?
Final product.
It gives product. But what do we reform here? Plus what? Plus hydroxide. Catalyst reform. But see, this water over here, that's where we generated the water ultimately. You might say, well, didn't we generate it here? Yeah, we did, but then it became hydroxide again. At this point, the water we made over there is gone. But here, this water is there at the end. So this is where we actually see that we're left with water. And the hydroxide is just a catalyst. Anytime you make pi bond kick off, okay, so that's important here. Before you're like, well, is that a good leaving group? Is OH a good leaving group? Not for SN1, SN2, E1, E2, in which the leaving group leaves in the rate determining step. But in these fast steps like this, anytime you make pi bond kick off leaving groups, easy to do. We said that lots of things can be leaving groups. This is a fast step. The rate determining step to this process is more deprotonation. This just, there you go. So ultimately, what do we make here? We make the alkene. And if you look at the alkene, the two carbons that become the alkene, what were they originally? One carbon was an enolate. It comes back right over here. What were they originally? One carbon was an enolate anion. The other carbon was a carbonyl carbon. Now, which carbon was the enolate carbon of the two? The one next to the carbonyl. Enolates are next to carbonyls. If they ain't a carbonyl next door, they ain't an enolate anion. And the carbonyl next here is there. The other carbon is a carbonyl. See, that just used to be double bonded to O. It's almost like the Vidic. Used to be double bonded to a phosphorus, now or the other way around. The enolate carbon ends up double bonded to a carbonyl carbon, but of the two, which one was originally an enolate? The one that has carbonyl next to it. We'll pick up on that on the next page. Questions about aldol reaction. This is a symmetrical aldol because it's sort of two reacting with itself. Now the product is not symmetrical. The symmetrical comes from the fact that it's two of the same reaction. You can also do this mixed, in mixed aldol. This is where it's two different reactants shown below. But you got a potential problem here. Potential problem. We try to react benzophenone with this aldehyde. What's the name of that aldehyde, by the way? Propanol. AL. Not propanol, that's an alcohol. Now, nomenclature video. Try to do this reaction, you're theoretically going to get 4 different products. Quite messy. Here's my product. I have 4 spots on TLC. How am I going to purify this? Maybe I get lucky and one of them will recrystallize or crystallize selectively. With 4, that becomes less and less possibility. How do we get 4? Well, how do we get this product?
You reacted with itself.
This is where this enolate reacts with itself. We just did that above. How do we get the product on top right?
The aldehyde reacts with the alpha carbon of the other one.
Top right. Which one's acting as an enolate?
The ketone.
Ketone, because that was originally an enolate carbon, because it's next to carbonyl. This carbon was originally what?
Aldehyde.
Carbonyl, and that's the aldehyde, yes. How do you get this one here?
The aldehyde.
Here's your alkene. Which carbon was originally an enolate, top or bottom? Top. And if you break it apart, and that's the enolate, that's the aldehyde acting as an enolate. And what did it attack? It attacked the ketone. How do you get the one on the far right? Bottom right.
Aldehyde reacts with itself.
Aldehyde reacting with itself. One of the handouts, I think the set, all the miscellaneous things were a white handout. I don't know if I still have it. I think I might have taken it out. Yeah, I took it out. I had a good number. It's a magazine article ad a chemical company has. They're showing this reaction right here. It's kind of where I got it from, I think. I don't know what they're selling, some type of base or something. They show the 4 products, but one of them has an error. It's not the right structure. And it's like, who put this ad together? Okay? But I used to say, hey, can you identify which one's wrong? But I think I took it out because I replaced it with something else. I think what they had is one of them was missing the alkene. It was just an alkane. Okay. But we can, now you could, once we learn what I'm going to tell you on the next page, you could say, well, should this only going to be 2? And I say, yeah, because you're recognizing that there is reasons where you could get selectivity here. But if there's no selectivity, you see how there could be 4. How can we get selectivity here? Well, the reaction over here is a mixed aldol. And it actually gives a good yield of the product shown. And where's your enolate? Let's do this instead. How many theoretical products could you form here? Could you also get 4?
No, you need 2.
I see a reason where you only get 2. Why is that?
The ketone can react with itself, and then the ketone reacts with the aldehyde.
That's 2. Why not 4?
Because the aldehyde doesn't have an alpha carbon.
Exactly. The aldehyde does not have an alpha CH. So you can't make enolate here. So that's going to cut your theoretical number of products in half to 2. The only place to make enolate is right here. By the way, is there any other chemistry that could take place here other than an aldol reaction? Because as we move along more and more, you're going to have to assess chemistry in a broader context. We're not just doing aldol, aldol, aldol like this, but you see something like, okay, I know 100 reactions. What could take place here? Is there any other chemistry that could take place here other than the aldol that we're doing right now? Anybody propose anything?
A hydroxide attack a carbonyl.
Okay, I was thank you. That's what I was. So is that going to lead to anything? Which carbonyl do you want me to attack?
Can it attack either?
Yes. Okay. Let's attack this one. And that's going to give. Let's turn it up. That's minus, right? We got an H and we got hydroxide. Okay. Possible. What's this? What would happen next in this mechanistic?
Electrons come down and just kick the hydroxide back off.
Exactly. Could anything else happen?
I think so.
Yeah. This is certainly possible. But this, anytime you can remake carbonyl, that's what's going to happen. This is just going to come back down and kick that back off, and you're going back here. Now that's hard to judge equilibrium because that's not an acid-base reaction. In acid-base, we can judge equilibrium using the pKa. But I'll tell you that what's favored here is going to be more the neutral carbonyl. Even if not, even if this is favored, this is an equilibrium. At the same time, you're going to get this. And if this reacts with this, that would remove this from this equilibrium. And so what would happen to this equilibrium when that gets removed from it? It would adjust this way. So even if this was more favored, it would adjust this way because this is consuming it and you're going another route. There is one other reaction that I could see here in looking at it further. Anybody else see another possible side reaction other than Aldol?
Like a benzene reaction, maybe?
Benzene's difficult. Usually requires high temperature, especially with hydroxide, like 300 degrees, high pressure. Aldol typically will occur at room temperature. I didn't say heat or anything. So theoretically, yes, but under conditions, I wouldn't. The benzene is a reaction where many other things would take place first. Hard reactions are not going to be occurring first.
Any gas?
Yes, explain.
There's a strong electron drawing group ortho-para to chlorine?
In my example, I've got a traditional leaving group on a ring, chlorine, with a strong electron withdrawing group, ortho or para. It is possible to maybe do an NAS here and substitute the chlorine. But I know this aldol chemistry, and I've probably done this exact reaction because we used to do these, we just vary the groups. You can do aldols and not worry about this getting kicked off. Because again, it's done at room temperature, mild, and the NAS requires a little heat. Most of the time, not always. But I just know that because I've done this reaction myself, right there, I've done that. And you get that product, the chlorine is still there. Here's the other thing. We're only using a catalytic amount of hydroxide. And so that's another reason. If you flooded it with hydroxide, the more and more hydroxide you add, the more and more likely you are to do that substitution chemistry. Okay. All right. In the end, there's often other reactions that may take place, and you can't always just be looking with blinders, especially once you get to maybe final exam time, because it could be anything. So how do I assess? Okay. So, this here, what's it going to attack? Another one of itself or the aldehyde? Now in this case, it attacks the aldehyde. Is there any reason for selectivity? Would it rather attack another of itself or aldehyde?
Alcohol,
Why aldehyde?
more electrophilic.
Yes, aldehydes are more electrophilic. Because if this was another R group, it would be donating. Aldehydes, the aldehyde carbonyl is more electrophilic. That means it's more prone to being attacked by nucleophiles. Now knowing that, this is where I would say, you might say, well, on the previous page you said 4, and we attack the ketone just like we attack the aldehyde. I'd say, yeah, theoretically 4. That's why I said you can make an argument for the previous page. It might only be 2 if you just only attack aldehyde. This one cuts it from 2 down to 1 because there's only one place to make enolate. Ultimately, the selectivity here is enolates here, and it attacks aldehyde. And if you work your mechanism, you should do that on your own, just like previous. But you need to be able to see how things are being put together here. You get a good product here. And by the way, typically, the alkene tends to be trans with the aldol reactions. Because there's nothing really pushing it towards cis. And trans is just more thermodynamically favored. And that likely just comes from rotation at certain points during your mechanism. Okay, groups here at some intermediate, they're going to be more prone to being here. And when you put your double bond in, groups are just more prone to being trans. Okay, so the aldol gives an alpha-beta unsaturated carbonyl. Recall, we've made such compounds before another route. How could you convert this to the same product with the alpha-beta unsaturated? What if we first treat it with maybe bromine and HBr? What will that do?
Create, you put a HB, you put a BR on.
What am I looking to do there?
You put a BR next to the,
Remember? Alpha halogenation under acidic conditions, just a mono. We can do a monobromination. Where if we were using basic conditions, it would be exhaustive halogenation. Then we come back with what?
LDA and carbonate.
Sterically hindered base, what would that do?
It would make it
E2 elimination. Okay. So alpha halogenation. Remember we looked at that sequence as a way to make an alpha beta unsaturation next to carbonyl? Yes. But here we had to have the entire sort of molecule already put together, and then we put in the double bond. The power of the aldol is it brings together two different molecules, two different substantially sized molecules to make it. But the problem is with you guys, you seem to sort of lose what's all going on here because it's just sort of big molecules. And lots going on up there. Where this is more sequential. Okay? But the aldol is very common. Very common reaction. Enolate reacting with carbonyl. Questions? Good? Now, the next section, we're going to be reacting alpha beta unsaturated carbonyl. What type of chemistry can you do here? That's coming. This is how you commonly make these types of compounds. Especially the aldol. But that there is very straightforward traditional chemistry as well. Okay. What do we have here? Intramolecular aldol condensation reactions. What type of product can we show here? You take this diketone, a little base, it's actually a catalyst. It will react and it will eliminate water. What will it form? Intramolecular reactions typically form rings. I agree.
a 6-member ring.
Let me show a product here. First one, where do you want to make enolate at? Or anything. You can add decarbonyl. That's not going to lead to anything. We talked about that. The other is enolate chemistry. Where do you want to make enolate at? Say it again.
Beta position next to proton.
Beta position?
Beta
Alpha.
Alpha position.
Do it on the left because on
Alpha position to a carbonyl. Well, first of all, which carbonyl?
the left, because the right.
The answer is either.
When with
It's either. They're the same.
or,
The question is, just choose a carbonyl. Which side of the carbonyl do you want to make it on? Because if I say here, well, that position's the same. If I say there, well, that position's the same. You got to see that. So let's just focus here. Would you rather make it here or here?
left.
The answer is really either. It's all in equilibrium. It comes from considering the next step. What size ring do you envision making here?
6.
6. I see 6. Well, what's the alternative size to consider?
4.
4, yes. And we'll show 6 and 4. Which is going to be preferred, 6 or 4? 6. 5 and 6 are your best size rings. How do we get a 6-membered ring? You make enolate here. I'm not doing full mechanism, okay? This is, everybody can show mechanism for making enolate. What can this attack? Here. Electrons up. This is your intramolecular reaction here. What does that give? What size ring? 1 carbon, 2, 3, 4, 5, 6 carbons connecting here. Okay. I'm going to just draw a 6-membered ring because I see that's what we're getting. They're all carbons. We've got to somehow have a starting point. I'm going to put carbonyl here. And then there's three carbons, 3 methylene groups, 3 CH2s between the carbonyls. 1, 2, 3. That means the other carbonyl is here. But it's not a carbonyl because when we attack it, electrons up. So it's going to be, let's call this, well, before I label it, let me quickly get there. This is the bond we just made. And the enolate, let's call this A, B, C, D, E, and F. Okay? A, B, C, D, E, and F. A attacking F. A, which is enolate next to the B carbonyl. A attacked F. We made that bond, and the electrons moved on to oxygen. What else is on F that I don't have there now? Methyl, don't forget about that. Is everything good over there?
Yes.
So you got to see how you're putting it together. Okay? Finish it up. You know mechanism. Can you finish it up and show product? What happens in the aldol mechanism?
The oxygen takes action.
Oxygen attacks water or whatever.
What eventually, just go ahead, show product, and then let's see if you got it right. What is the final product here after you complete after you eliminate the water? Aldol gives what type of product? Alpha, beta, unsaturated. So make sure you have that in your product. That's what it gives. Somebody got it? I think that's it. Your ring is just a little. You got a short bond and a long bond, but I think it's 6-member ring. It looks like 5. Yeah. Okay, final product is going to be double bond here, and draw this right. On this carbon, there's a methyl. And let's try to make bonds connect. That's a 6-member ring, right? Is that right? We just made the alkene. Here's your alkene. It's alpha, beta, unsaturated with carbonyl. There's the carbonyl, alpha, beta. Aldol gives what? That was originally the enolate carbon. We know that because it's next to carbonyl. The other carbon was originally what? The other carbon was originally a carbonyl, but that carbonyl is now gone, and that oxygen was lost as water, ultimately. Because originally you had a 1 carbonyl, then 3, and then that was a carbonyl originally, ending with a methyl. What would the 4-membered ring have looked like? And we're out of time. On Monday, had the 4-membered ring. Let's see what it would look like. Just as practice. Think about that. But the 6 will be favored. And then please be looking ahead. We'll start reacting these alpha beta unsaturated in what's called a Michael reaction. Michael reaction. See some of you in lab this afternoon. Group name on the board. You can turn in